Yes, sure. So, good morning, everyone. On behalf of Jyotirvidya Parisamstha, I welcome you all to the inauguration lecture of our basic course in practical astronomy. So, let us first know more about this basic course of practical astronomy from our volunteer Sarang. So, can you please tell us about the course? Sarang?
We can still hear the stream.
Okay. I don't know. Actually, I have turned off.
So it must be coming from somebody else's voice feed.
Okay. Let me mute it and let me turn off my speaker also. You can continue. Let's see. I will just check.
Yeah. Okay. Thank you, Avantika. This is Saranga Vandana, Executive Committee member of Jyotirvidya Parisamstha, and I'll just briefly talk about basic course in practical astronomy. JVP has been running this initiative since many years now, and even if we call it basic course in practical astronomy, we delve quite deep into various aspects of astronomy. So there are various lectures that we have, and we begin right from history of astronomy and basic awareness about solar system and celestial bodies. And then we touch deeper aspects like positional astronomy, time measurement, and calendar systems. And since astronomy is all about practical activities, we discuss various instruments and equipment used in astronomy, as well as multi-wavelength astronomy, various exercises and activities that participants can do. Some theoretical aspects like cosmology, supermassive black holes, gravitational wave detection, etc., radio astronomy, and so on. And we are very fortunate, we are very privileged to have speakers from renowned institutions like IUCAA, NCRA, IIA, and others, in addition to speakers from JVP, in-house speakers from JVP. So this year we are having the second batch of BCPA. First batch is already over and second batch has just started. So we are very excited. So a warm welcome to all the participants to BCPA, as well as a warm welcome to our YouTube viewers. And you can still join this course if you are interested. You can visit our website, jvp.org.in, or you can also check our Facebook group, JVP Jyotirvidya Parisamstha, and get in touch with us, and you can enroll for the course. So with that, I'll hand it over to Avantika again to introduce our speaker. Thank you.
Yes, sure. So last month, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics to 3 black hole researchers, Dr. Roger Penrose, Dr. Reinhard Genzel, and Dr. Andrea Ghez. Professor Penrose got half the prize for his theoretical work on black holes, while Professor Genzel and Ghez got their prize for showing that supermassive compact object is present at the center of a galaxy. To discuss their work and research in detail, we have Professor Ajit Kembhavi, former president of IUCAA, with us today. Professor Kembhavi did his PhD from TIFR Mumbai and was a postdoctoral fellow at the Institute of Astronomy, Cambridge. He is an emeritus professor at Raja Ramana Fellow at the Inter-University Center for Astronomy and Astrophysics, that is IUCAA, Pune. He was a director until August 2015. He is a vice president of the International Astronomical Union. He is also a former president of the Astronomical Society of India, the Indian Association for General Relativity and Gravitation, and the International Virtual Observatory Alliance. He is fellow of the Indian Academy of Sciences and the National Academy of Sciences, India. He is a distinguished astronomer who works on galaxies, quasars, and other extragalactic objects. He has published a large number of research papers and several books in the same field. He is involved in many international collaborations and for several years being involved with the 30-meter telescope project and LIGO India. He is now on the apex committees of these projects. Professor Kembhavi is the president of Jyotirvidya Parisamstha from 2018. Sir, we are honored to have you today with us. So I now request Professor Kembhavi to take over the charge. Thank you.
Thank you very much, Avantika, for your introduction. You've done it very well. And I'm now going to begin my lecture on black holes with particular reference to the 2020 Nobel Prize in Physics. So, as Avantika has already told you, the prize was shared between three people. When this is done, sometimes you'll find that all three people share the prize equally. But if there is a but there are occasions where the work is slightly different, or somebody may have worked more, and in that case, the prize is shared in different proportions. So Sir Roger Penrose got half the Nobel Prize, and then the other two, that is um, Reinhard Genzel and Andrea Ghez, got the other half. Reinhard Genzel is the director of the Max Planck Institute for Extragalactic Physics in Munich. Andrea Ghez is at in the US. So now these two people worked independently on establishing the presence of a supermassive compact object in the center of the galaxy. It is widely believed to be a black hole, but the Nobel Committee doesn't mention that simply because it has not yet been incontrovertibly decided that it is a black hole. But what we know is that there is a supermassive compact object there. Now, it's a remarkable set of observations which have been required to establish this, and these were done independently by these two groups. Genzel is situated in Europe and therefore use European facilities, being large optical telescopes, near infrared telescopes, in, in the European Southern Observatory, which is located in Chile. Andrea Ghez, being an American working in an American university, she used American facilities. Again, located in Hawaii, and she used the Keck telescopes and other telescopes to do her work. Both of them were supported by large teams, and then the team members kept changing, because you will find that the work has gone on for a period of about 20 years. And it's so remarkable that this result could be obtained at all. And it is very reassuring that two different groups working independently came to the same result with astonishing overlap in the observations, in the observational points, as I'll show you during my lecture. I'll begin with considering the theoretical aspects of black holes, because that is because Penrose got his Nobel Prize on that, and then I'll go on to the observational aspects. I'm sure that many of you really are familiar with what are black holes. That has become a part of the normal folklore now. Everyone knows a little bit about black holes, which was not the case even some years ago. Now, here is a picture of a black hole which should be taken. If you are, let's say, the isolated black hole somewhere in the galaxy or in the extragalactic universe, because a black hole by definition is black. It is not as if because of some network problem you are not seeing an image here. This is what you see if you try to obtain an optical image of a black hole or observe a black hole in radio or whatever. So if it is a completely isolated black hole sitting quietly there. So how would we know that such a black hole exists at all? We would know because of its gravitational effects. Because the black hole has mass, it could also have other properties like spin and charge. Just these two properties, nothing beyond that. But a black hole has mass, and therefore it produces a gravitational field. That would again be a static gravitational field. But imagine that there are two black holes going around each other, and then they'll be emitting gravitational waves, which also, as we all know, have now been detected. But then before that, the detection of gravitational waves happened as late as 2015. But before that, people have been seeing black holes or establishing their presence through other observations. For example, here you see that there's a very nice picture here. You would have seen such a picture many times before. So what happens here is that there's a black hole sitting here, and then there is a star in the neighborhood of the black hole, and matter from the star is being attracted by the black hole. Now, this really can't happen certain special conditions are required for such a thing to happen, but those are obtained many times in a galaxy. So you see matter being pulled in. The matter comes in with angular momentum, therefore it does not fall straight into the black hole. It keeps going round and round and round, and a disk of matter is established. And matter in this disk gradually seeps into the black hole. And then that matter falling into the black hole releases energy, not and then that energy can heat up the matter in the disk, and also it sets up other complex interactions which lead to the formation of jets, for example. And such a system can be observed in the X-rays. That is how such systems are discovered, or in the radio or optical or whatever. Depends upon the detailed circumstances. Now, such black holes are called galactic stellar mass black holes because these black holes have masses in multiples of the solar mass. So, like 10, 15, 20 solar masses, like that. And then uh, they are products of the evolution of stars. Now, the problem here is that it has not yet been established that these objects, compact objects which are there, uh, are actually black holes. Meaning that I could take out this object and a black hole from here and introduce a neutron star, which is also a massive compact object. Then what you would get from the system would be quite similar to what you get when a black hole is present. There are differences of detail, but those differences are not so great that the presence of a black hole can be completely unambiguously uh, established. But nevertheless, we do feel that there's a black hole because of all the evidence which has piled up. Now, here you see another beautiful picture, and this is what happens when you have a supermassive black hole, which typically occurs in the centers of galaxies. So again, because matter surrounding the black hole goes into a disk around it, and then um, the disk as the matter in the disk gradually seeps into the black hole, then energy is emitted, which typically leads to the formation of jets, and then you get what is known as an active galaxy. An active galaxy meaning a galaxy which is emitting energy, very large quantities of energy, which is not coming out directly from the stars which are contained in the galaxy. Now, here you get what is known as a supermassive black hole, because the mass of such a black hole ranges between millions of solar masses to billions of solar masses. So these are two families of black holes, but now several other kinds of black holes between those are known, etc. But I'm not going into those details. Now here is a third picture of a black hole. Now this is not really an image of a black hole. The other two were not really images taken observationally, but they were depictions of what you expect is happening around a supermassive black hole or around a stellar mass black hole. Now, this diagram, which was first developed by Roger Penrose, and is named after him. So, this is a mathematical representation of a black hole in coordinates, in certain specific coordinates. So, the black hole itself here, which we all know is a point object. It has got mass, but it has got no size. So, a black hole here is represented by this blue line here. So why the black hole become a line? That's simply because in this diagram, space-time gets stretched in different ways in different locations. And then, a lot can be inferred about the mathematical aspects of the space-time around a black hole through the study of this diagram. And one striking feature that you see of the diagram is that everything that is shown is to the right of this red line, and there's nothing to the left. And there, you geometers know that that is not a realistic situation. If I got this line ending here, why is it ending here? This line is ending here on the blue line because this is a singularity. But this other line is not, there's no singularity along the red line. So it's possible to produce this line further. And when you do that logically, then you get a reflection of the diagram that we're seeing here. So there will be a blue line at the bottom like this, and everything else is reflected in the red line. And that is known, I shouldn't use the word reflection, not exactly reflection, because the blue line comes here, the right-hand side goes to the left-hand side. so like a double reflection. And then you get the bottom part represents what is known as a white hole. So the black hole, white hole pair, right? Now let us go to Newtonian black holes. And again, most of you would have heard these analogies. And because in Newton's gravity, now gravity is attraction between universal attraction between bodies, g m1 m2 by r square. These are the masses. This is the distance, inverse square law. And you have got the minus sign, which is very, very important, which says that gravity is a attractive force. So if I now stand on the surface of the Earth, I don't have to stand at the North Pole. This is convenient here. So it just shows like that here. And then I throw a ball up. Then how high the ball goes depends upon how much energy is given to the ball. So what is the starting velocity of the ball? Right? So using Newton's mechanics and Newton's law of gravitation, one can work out the relationship between. So, so what is the height which is reached? It will be depending upon how much velocity is given to it. And then the question is, what is the velocity which is required so that the ball completely escapes into outer space? It will never come back. And then, as many of you will know, that velocity, which is known as the escape velocity, is given by v is equal to square root of 2 times g times m by r. It's a very simple expression. So if I put in the mass of the Earth and the gravitational constant and the radius of the Earth, then I'll get an escape velocity of 11.2 kilometers per second. Right? So now you see, if I go on increasing the mass, the velocity will increase. Or if I go on decreasing the radius, again the velocity will increase. So now the question is, what is the velocity? What are the circumstances required so that the escape velocity becomes equal to the velocity of light? And it is trivial to show that the radius for a given mass, the radius must be equal to 2gm by c square. Now, at least some of you will know that this quantity 2gm by c square is known as the Schwarzschild radius. Now, if I if I take the Earth is a given object, if I take a similar object with the same radius and go on increasing the mass, then you will find that the velocity for a given radius, the velocity increases. If I decrease the radius, again the velocity increases, as I already told you. And now this particular fact was first noted quite a long time ago by John Michel in 1784. So what did he say? He said that a body with the same density as the sun, but 500 times larger in radius, would not allow light to escape from it. So you see that because I can play with the mass, I can play with the radius. So here the density is held constant, but the radius is being increased. So the mass goes on, the same density there, so the mass goes on increasing. And when this condition is met, that the radius becomes 500 times the radius of the Earth, then even light cannot escape from it. Right? So this is the first intimation that there's something called a black hole, which is Newton's theory. And about a decade after that, Pierre Simon Laplace, who was a great French mathematician, he is known to everybody who's done a paper in mathematics in BSc, physics or mathematics in BSc and MSc. And then he also made the same statement, which says that I have to move these things around. I won't read the statement because I cannot see it because it's been covered by these things here. So, but Laplace said basically the same thing. But even though you can get these black holes in the sense that light cannot escape from an object, suitable object, you still find that nobody was worried. That is because in Newtonian physics, there is no limit on the velocity that a body can reach. There's nothing specific about the velocity of light except that it is the velocity of light. So I said that, all right, I can put a torch on a rocket and I can shoot up the rocket and then I light the torch. So the velocity of the light there will be equal to sum of the velocity of light when the torch is at rest plus the velocity of the rocket. So it should be more than 3 to 10 to the 5 kilometers per second. So it will escape. right? So there are no issue. The big problem started when people considered black holes in general relativity. Now, I cannot go into the details as to how it all happened, but I just want to give you just a gist of it. Because again, I'm sure that everybody is familiar with this thing, that the general theory of relativity is a theory of space-time structure. So here I should, of course, first introduce the special theory of relativity, again due to Albert Einstein. So which was also a theory of space-time structure, but it said that three dimensions of space and one dimension of time are combined together into a single four-dimensional entity, which is called space-time. And that leads to all kinds of situations like velocity of light is the same in every frame of reference. Nothing can move faster than light, and simultaneity is relative. Then you've got E is equal to mc square and so forth. But there, space-time is rigid. But when you go from the general theory of relativity, you go from the special theory to the general theory, Einstein made space-time dynamic. Okay, meaning that uh, the presence of matter and energy curves space-time. So if there's a different distribution of matter, the curvature will be different. And then all the particles, massive particles and light rays, move in the curved geometry, and their trajectories would follow paths which are in the Newtonian approximation similar to what we see. What do we mean by this? When the mass of the object is not too large in astronomical terms, then Newtonian gravity still prevails because general relativity reduces to Newtonian gravity. And then, for example, Earth would orbit the sun as it actually does. But when we go to other situations where the mass becomes very large, so that the curvature becomes very large, then all kinds of new phenomena come into the light. So, Einstein gave a set of equations which are named after him, which are very complex. These are 10 independent, very complex, highly coupled uh, tensor equations. And then below that, you have got this equation, which is known as a geodesic equation, and which shows how particles move in this space-time. So, solving these equations, in principle, uh, the entire physics of general relativity can be developed, right? So now Einstein did this in 1915, and he then obtained approximate solutions of these equations. And having done that, then he made these three predictions, which I'll come to again towards the end of my lecture. But then, what I'm more interested in here is that in 1916, the great astrophysicist uh, Carl Schwarzschild gave an exact solution of Einstein's equations. And let me see if I have it here. Yes, there it is. Okay, gave an exact solution of Einstein's equations. And this is known as the Schwarzschild solution. I'm unable to describe it to you, of course, explain it to you what it means. Um, but this is the exact counterpart of a Newtonian field around a point mass. So if I take a point mass with a then then the field at any point is given by Gm, the force per unit mass at any time is given by Gm minus Gm by r square. So here you've got a point mass, but now it has to be considered within the framework of general relativity. When you do that, you get this expression for the structure of space-time. And then if I say that, you see what will happen is that at r is equal to 2 gm by c square, this particular radius, you'll see that this quantity vanishes and this quantity becomes infinitely large. So that leads to all kinds of problems. Okay, so that is where the concept of the black hole comes from. So, what is the general, what is Schwarzschild interpretation? Please, you must understand that he did not call it a black hole. That name actually came in the late 50s and early 60s. And Schwarzschild just discussed his solution. And you see that you've got a point mass here, and these are the field of the point mass in general relativity. And when you go far from this object, you'll get a field which just reproduces all the results of Newtonian gravitation, because the gravitational field is weak there. But when you come close together, new effects begin to show up, and that r at the radius is equal to 2 gm by c square, uh, which is equal to the Schwarzschild radius of the sun, Like if I take the mass of the sun here, then the Schwarzschild radius of the sun is about 3 kilometers. So if the sun were, if it compressed to a radius which is about 3 kilometers, it will collapse and form a black hole. Even after, before that, it will collapse, of course. But at r is equal to 3 kilometers, there's a surface which is not a real physical surface, and which is not the Schwarzschild surface. And then that is also known as the event horizon. And why is that? Because any nothing inside can come outside. Because any object which is inside, for it to come outside, the velocity of light would need to be exceeded. And since that cannot be done, nothing can come out. And so the inside and outside, things from the outside can go inside, but things from the inside cannot go outside. Right? So this is a very strange situation. There also other major problem here. I told you that here there is an event horizon, but at the black hole itself, then there is an infinitely large gravitational field, and which means that the space-time uh, curvature is infinitely large, which means that the concept of space-time no longer exists. So this is a really, really terrible situation because there's a complete breakdown both of the physics and of the mathematics and the geometrical structure of space-time itself. So that becomes a very major problem. How do you deal with it? Now, quite a long time after Schwarzschild, nearly 50 years, in 1963, another black hole solution was developed by Roy Kerr. And what is so this is known. This is the solution for a black hole which has got spin. So you see that we you can imagine that the Earth is spinning and the Sun is spinning because they've got finite radius. So they're rotating around an axis. But this has got zero radius. So what do you mean that it has got a rotation? Then the indirect answer to that is that's exactly what happens to an electron. Within atomic theory and particle physics, an electron has got zero radius. A proton does not have zero radius. A neutron does not have zero radius. But electron has zero radius. But nevertheless, the electron, you see, is spinning. And that was discovered by Pauli a long time, predicted by Pauli a long time ago. So just as an electron has got a spin, a black hole also has a spin. And the consequence of the spin is that the event horizon becomes very complex, and then there's another horizon which is known as the ergosphere. Right? So I'm just showing you this picture. I'll quickly move out of it, which shows that the situation is far more complex than it is in the case of the Schwarzschild black hole. So whether you have got a it distorts the trajectory of the particles and light because in Einstein's theory, gravitational bends a beam of light like this. And so if the beam of light is close enough to the center of the black hole, then it can get trapped and keep going round and round and round, exactly at the same radius forever and ever. So if there's the light falling out of the black hole, then you can get a, a photon sphere. And some of you, or maybe all of you, because a lot of publicity, would have seen what is called the first direct image of a black hole, which was published sometime in the month of May this year. And the image that you see there is a consequence of extreme light bending because of the very strong gravitational effects. Right. So what have I told you now, and what was learned from 1915, 1916 until now? Let's say all of this was known by the 1960s. So a black hole has infinite matter and curvature density. I should actually say infinite matter density and curvature. So the question is, how do we deal with these singularities mathematically? Because there's a breakdown of space-time structure. So what do we do there? How do we define all these things? Then are they just solutions of Einstein's theory, or do black holes really exist? Because then why would we doubt their existence? You can say that, look, a Schwarzschild solution is an idealized solution. There's a point particle which starts a spherically symmetric object, then collapses, let's say. Or we could say that there's a point with spinning, which also has axial symmetry. So are these are these black holes, are these solutions occurring simply because of these very idealized, highly symmetric objects? Because highly idealized objects with very high symmetry. And real life objects will never be like that. There'll be deviations of symmetry. And will those prevent the black holes from occurring? You know also that our expanding universe in the Big Bang theory came from a single point long time ago, many billions of years ago. And when it was a point, the matter density was infinitely large, the curvature was infinitely large. So, but again, this kind of a curvature, we know situation we know occurs in the standard models of the universe, where the universe is assumed to be completely homogeneous and isotropic, means very highly symmetric. So, but the real universe has got all kinds of asymmetries in it, and would those prevent the singularity from occurring? Then have black holes been observed? And of course, how do you deal with Big Bang singularity, which I've already told you about? Now, one question now is fully answered, meaning have black holes been observed? Yes, they have been observed. And then we do not have to depend on this strong but yet uh, not fully established evidence which comes from astrophysical situations. I mean, the kind of astrophysical situations which involve a black hole sucking in matter from the surroundings. But here, what happened, as you all know, that in 2015, the LIGO detectors actually detected a black hole merger, which was announced in early 2016. And so what happened was here was that there were two black holes which were going around each other. They were spiraling. And such a spiraling system must emit gravitational energy. As the gravitational energy goes out, the total energy of the system becomes negative, and which leads to a shrinking of the system. As the system shrinks, then it moves faster and faster and emits gravitational energy at a higher and higher rate. And eventually, in finite time, the two black holes should come together, merge to form a single black hole. So there will be a burst of energy, after which nothing should happen. And remember that these are two isolated black holes just going around, but there's nothing in their neighborhood except the other black hole. So neither the black hole emitting any radiation, optical radiation, radio radiation, etc. It's no electromagnetic radiation of any kind. And when they merge, again it is the same. You will not get any radiation, which means that this will be a completely, as far as electromagnetic theory is concerned, is a totally silent situation, right? So then what do we do? But we can detect the gravitational waves. And the gravitational waves have got a very beautiful pattern. And this pattern, you see that the gray pattern that you see here, uh, and which is a reconstructed wavelength, and the red one is numerical relativity. And but these are all based on the data that you see here, the reconstruction. So there's the data on the top panels, and this is the smoothing out of that through the models. And then you see that as the black holes are coming closer and closer, the frequency keeps increasing. This is the frequency of the gravitational wave which is detected until there's a merger. And then there is this situation which is known as a ring down. And this kind of a ring down was first studied by Professor C.V. Vishweshwar. Okay, in 1970 was the paper was published, I think. Right, so you see that this observation and then many more observations of these binary systems merging, both black holes as well as neutron stars have been detected. Now it is common knowledge. So we no longer have any doubts about the existence of black holes. But the theoretical challenges still were there. So now, the work of Roger Penrose, for which he was awarded the Nobel Prize, uh, has done quite a lot, a great deal, to uh, see how to deal with black hole singularities. So before I do that, I should say that there is that Penrose, the work of Penrose, and later by Hawking and Garrosh and others, depended very heavily on work which was done by Professor A.K. Raichaudhuri. Now, many of you would have heard of him, of course. So he was a professor in Calcutta, And in 1955, from 1953, he did this work on what is known as the Raychaudhuri equation, which it was derived in the cosmological context, and but then it applies to all sorts of situations, and that was used by Penrose and Hawking in the work. Now, similarly, uh, when we talk about the black holes and supermassive black holes in the center of the galaxies, a prediction that such a black hole exists was first made by Fred Hoyle and Jared Garlick. So they wrote a paper in 1965 where they discussed the existence of a very massive object at the centers of galaxies. Now that work has sadly not been as much recognized as it should have been, uh, and it has again played a very major part in establishing the notion of supermassive black holes. So what did Raychaudhuri do? So he considered, I have to keep moving this around. So he considered how a fluid which is moving around a black hole behaves. So why do you want to consider a fluid? Because you see there are all these galaxies in the universe, and in cosmology you treat each galaxy as a point particle, and then you want to see how these point particles are moving. So Raychaudhuri equation deals with the flow kinematics generated by matter moving freely in a gravitational field, and then it takes into account the expansion uh, of these trajectories, which actually corresponds to the expansion of the universe and what is known as shear and what is known as the rotation and acceleration. So then, just like I showed you Einstein's equations, so here is a very remarkably beautiful equation, which is known as the Raychaudhuri equation. The Raychaudhuri equations, of course, are multiple equations, which also tell you how the shear and the uh, rotation evolve, but I have not put those down. And this tells you how the universe is accelerating, and it shows you that gravitation is an attractive force, and this term tells you that if there is shear, that will be attractive, and this tells you that if there is rotation, then there will be a repulsive force, and this is the effect of the cosmological constant. So it's a remarkable, you just see how beautiful the equation is. And in order to understand it, of course, you need to know more advanced mathematics, which I'm sure some of you at least will be going into at a later stage in your life. And then this is a paper in which called Relativistic Cosmology 1. And you see it was published in 1955, but it was received in 1953. Right? Now I just want to mention this. I cannot do anything more than that. So the stage was set for Penrose, where the understanding of black holes were had uh, had taken place because of the work of Meissner, John Wheeler, and his younger collaborators, Meissner and Thorne, and a host of others, uh, many many uh, many mathematicians and physicists, and things are becoming clear. Penrose himself was a mathematical physicist, and then in 1965 he gave what is known as Penrose's singularity theorem. And he says that he put down certain very general conditions for space-time. And then he put this convergence condition, which came from Raychaudhuri equation. Uh, then he said that if such a thing happens, then then there must be future incomplete null geodesics. And so, what does it mean? It means, in very simple terms, that a singularity must exist in such a space-time. So therefore, Penrose's theorem says that the black hole singularities that you see really are not the consequence of any very special conditions. So it was the first theorem, but then many people worked on it. And here I'm just highlighting the new concepts which are introduced here for all this future trap surfaces, incomplete null geodesics, and so forth. So this was extremely profound work. And one of the review articles I read recently said that this was a true departure from Einstein's thoughts. It is not a departure from general relativity. But when you give a great theory, then there are many things hidden in it which may not have, which the creator of the theory would not have thought about. Right? So Einstein worked on the theory and interpreted it in a certain way, but this global way of looking at it probably was not conceived by him then. Okay, this is the first real departure uh, in general relativity from Einstein's way of thinking about it. And then, quite immediately, various other people also worked on it. And you see here this very beautiful photograph, Stephen Hawking and Roger Penrose. This was not the time that they were working. You see them here as very senior people. And then there were others also. And there was Robert Garrosh from Chicago. And then there was George Ellis from South Africa. And much of the work that was done was summarized in a book, which is called A Large-Scale Structure of Space-Time, uh, by, by Hawking and by Ellis. Now, these books, that book, as well as the book called Gravitation by Misner, Thorne, and Wheeler, they came out in the early 70s, just as I was doing my PhD. And so I had the great privilege of learning these subjects from these beautiful books. Okay, so I cannot go into any further detail about the work concerning theoretical work concerning black holes. I hope to do that sometime in a larger number of lectures. But here, uh, now we go to the second part of the prize, which is a supermassive object at the center of a galaxy. So here you are more familiar grounds. Now you know a galaxy is made of billions of stars. Our galaxy is 10 raised to 11 stars. That's more than about 100 billion. And then what you see in a galaxy is typically the sum of the output from all the stars in the galaxy, as well as the gas and the dust in the galaxy. But there are some galaxies which have extraordinary properties. For example, here is the galaxy, and so at Centaurus A, where you see these large these lobes of radio emission coming out of it. So if the GMRT looks at Centaurus A, this is the kind of picture that it would make of it. And the actual optical galaxy is sitting somewhere here. They're much larger than that. And you see these jets coming out. Then there are other curious phenomena. For example, there's another galaxy called M87, active galaxy. Then there are these are jet from the active galaxy. And this small little part here has been magnified. And then there are these two knots which are separating. And this is in 1994, this is in 1997. So these two knots are separating. And because you know the distance to the galaxy, you can figure out what is the velocity of separation. And that comes out to be several times the speed of light. Now, we firmly believe in special theory of relativity, and therefore we cannot believe that anything can move faster than light, and that indeed turns out to be true, as first um, talked about by Lord Martin Rees when he was a graduate student in Cambridge. So the idea there is that these objects are not separating at speeds exceeding the speed of light. They're only approaching the speed of light. And then the rest of it is simply a projection effect. So if they approach the speed of light, then it would mean that there must be an extremely strong gravitational field present, because otherwise the gravitational field would not have been able to contain them for any period of time at all with such high speeds. And so one can then infer, as Professor Lyndon Bell and others did at that time, that there must be a supermassive black hole which is involved at the centers of this galaxy. So, there are reasons to believe that such black holes could also exist at the centers of normal galaxy like ours. And there are different techniques for looking for black holes, and people have indeed used these techniques to establish that these black holes exist in tens and possibly hundreds of galaxies. So our general belief is that there are these supermassive objects at the center of all galaxies, if not all, most galaxies, let us say. So, does such an object exist at the center of our galaxy? So, here is a beautiful picture of our galaxy. And then many of you might have seen a galaxy in this form. You only have to look in the direction of Sagittarius on a dark night. And this is the central portion of a galaxy. This picture is a near infrared image of a galaxy, which is taken by, so it's a composite picture. You just point, so here, when you point here, you'll get the central region, and then you point it further away from the central region and make a collage. And then this is what you get. This still is not the whole galaxy because the outer parts become too faint to be observed in this manner. But then if you go from the center of the galaxy, if you go from end to end in the galaxy, then you get, you got a size of about 100,000 light years, okay, which is 30 kiloparsec. So the radius of the galaxy can be 15 kiloparsec, but you must understand it is not a rigid radius. The galaxy becomes diffuse as you go towards the periphery, and the stars gradually merges into extragalactic space. So what is very important for our purposes is the fact that this, you see this brown color thing here, which is basically dust which is present in the galaxy, which absorbs the light, and then it allows only the redder light to escape from it, and therefore you see the redder color here. So what we want to do is to see whether there's a black hole at the center of the galaxy. And how do we find that? I told you that there are various techniques, but the fact that this black hole is relatively close by. What do I mean by that? Look at Andromeda galaxy. It's about 2.2 billion light years away. Right? So that's quite a great distance. Whereas this center from us, because our sun is located somewhere here, about 8 kiloparsec, 24,000 light years away. So you see that the center of our galaxy is much closer to us than, let's say, the center of the Andromeda galaxy. So we should be able to observe things here. So if I observe the movement of stars, then can I use that, the way the stars are moving, to infer whether there is a black hole at the center? So that is the quest. What are the difficulties involved? Is that if you take the kind of stars which are there in the galaxy, and then you move them from 8 kiloparsec from us, then the stars will become extremely faint. There's also another great problem. The dust is present, and then you see, so you see that if you take a star to the center of the galaxy, the dust has to traverse through the star. The star is already faint because it is so far away. So then as it traverses through the dust, it becomes fainter still. Now you people know what's the magnitude. And because when you take a star from there to there, there's a loss of about 30 magnitudes. It's impossible to observe such a star. So then what do? First of all, you use as big a telescope as is accessible to you, right? Because you want to observe, because the stars have become faint. Secondly, you'd like to observe at higher wavelengths. Why observe at higher wavelength? Because the greater the wavelength, the less is the absorption in the galaxy by the dust. So I use higher wavelengths. Higher wavelengths meaning what? I would like to use near infrared imaging. I could use radio imaging, for example. I show you radio imaging, but stars don't typically emit radio waves. So here you use near infrared imaging, which is actually pretty difficult to do. And it's a relatively recent thing. It has been around for a few decades and no more. So here is the structure of the galaxy as seen from the top. This is a sideways view that we had. This is seen from the top. So you see the spiral arms and then the bulge which you have seen here. Right. So now I already mentioned this to you. We want to observe the center of the galaxy, and near infrared high resolution imaging is required. High resolution meaning what? Typically, the size, the resolution which is obtainable from the Earth is about 1 arcsecond, and that is because of the effect of the atmosphere, which spreads out the light from the stars. And in the most exceptional observatories and exceptional conditions, you could get, say, 0.5 arcseconds. But what you require is 0.1 arcsecond. And in order to do that, you need to apply techniques like adaptive optics. Okay, so you have to use that, which makes life very difficult. So now let us see what happens at the center, because you remember that optical pictures have not really shown at the center as such. And here is a radio map of the central part of a galaxy. And radio astronomers have known for some time that there is a compact source here to the center, which is known as Sagittarius A. Right, so this is a radio map at 90 centimeters, which is done in 1999. But similar observations, though not so precise, were available for a long time before that. Then, in 1974, there was an observation made by Balick and Brown in 1974, and who said actually that look, Sagittarius A that you see here, this Sagittarius A includes a source which is extremely compact, and they called it Sagittarius A star. Why A star? Uh, they said, oh, this is like the excited source, the exciting source, and because excited atoms are denoted by stars, so they use A star for it. And to think about this source, it was very compact, and it was not showing any motion at all. That was detectable with the accuracy available at that time. So they said, look, this is probably an extremely massive object because the more massive an object, the greater inertia it will have. So it will be less perturbed by its surroundings and therefore it will not show much motion. Right. So this is the story. Now, later in the thing, and the Chandra X-ray Observatory also made a mosaic, X-ray mosaic of this, and they also looked at Sagittarius A star. So you see that there's a very beautiful, you see this blob of hot gas, because Chandra X-rays are emitted by hot gases, and the hot gas is which is present there. Right? So now we come to the main part of the observations, and he said that look, so here in the galaxy, here are the stars in the galaxy, and now we want to go down the center. What is the kind of resolution? What kind of area do we want to cover? So you see this bar here, white bar to the upper left-hand side, and it has got a it has got a size of 6 light months. Right. So therefore, this area here is smaller than 6 light months, about 4 light months. And so, what is that on the scale of our galaxy? I told you that the galaxy total size is 100,000 light years. Right. So you come to 100,000 part of it, 10 to the minus 5, and that gives you 1 light year. And now this is 1/3 of 1 light year. Right. So you are gone really to the center of the galaxy, and you see that lots of individual stars there, which shows. And what is this image? Sorry, I want to move this out. So this is a HKL composite, meaning H, K, and L are bands in the near infrared, just like you got BVR in the optical. And so, and it has been, it's a HKL composite with special speckle and adaptive optics used to increase the resolution. And so now, I thought that there was one more picture, one moment. Yeah. So you see here, now this one here, which I was not seeing, maybe you saw it under the panels. And so this one, here's Sagittarius A star. So you really have got very close now. And now what we show here is the publication which was made by Shodel et al. So in APJ 2003. And what do we see here? That this is that part which I was showing you. And these are individual stars in that part. And these individual stars are named. This is S1, this is S2, this is S8. S2 is the star which has been followed the most and which plays a very important part in these observations. Now you see that this image is taken in 1995 and this image is taken in 2000. This paper, so you see that you're following the motions of the stars year by year by year. So you do it now, then you do it a month later, you do it a month later. It just shows you that the stars have moved. Now, you must understand that these are incredibly difficult observations because, as I told you, first you use the biggest telescopes, you use near infrared imagery, then you have got the spectra for which you use what are called integral flux units, then you analyze all the data. Now, it is difficult enough obtaining one image like this, but now you have got images over the years and you want to know whether these stars have moved there. But for that, what you require what is known as a fixed frame of reference, because it has moved relative to what. So you need a frame of reference which can be held very uh, rigidly, and that is extremely difficult to do. And the way they do it is that they use certain radio stars here, and these radio stars emit radio waves, and their positions can be determined extremely accurately using VLBI, and then that accuracy then is used to define the accurate reference frame here. So I'm stressing this point because there's incredible work which has gone into the final award, uh, the work leading to the award of the Nobel Prize. So now what you see here is these stars with these arrows on them, and the arrows indicate the magnitude and the direction of the velocity of this. So you combine different pictures and you have done this. Okay, so this size of arrow indicates 500 kilometers per second. So these are stars which are moving very fast. And then we come here to S2, and then this is Sagittarius A here. And now the orbit of S2 is now mapped like this. So you see that this is in 1992, 94, 95, and so on, 2001, and this is 2002. And what do you see from these positions? You see this remarkably beautiful orbit here because it is quite, you can very nicely fix, fit an ellipse to it. And then what happens? What is sitting here? There's a focus of the ellipse on which is sitting Sagittarius A star. You might be reminded here, because I'm sure that you have read here, that the shape of the orbit of Mars was first determined by Johannes Kepler. So he was provided the data by Tycho Brahe, whose research assistant Kepler was, and then he worked on it for a very long time, and then he got the shape of the orbit. He believed that the orbit was an ellipse, but he could not prove it because he did not know what was the equation of an ellipse. And it went on like that, and then finally he was able to establish that it is indeed an ellipse. So Kepler gave his three laws, okay, which says that the orbit of the planets around the sun are elliptical in shape, with the sun sitting at one focus. And then of course there are the other laws about relating the period and the distance, and also there's the law about equal areas being swept in equal times. So now we are moving 400 years into the future, and so what all these marvelous astronomers have done in their work is just the same. So they have looked at the orbit of S2, and then they have fit an ellipse to it, and they have shown Sagittarius is sitting here. But they can go one step further than Kepler was able to do, because Kepler, when Kepler did his work, Newton's work had not been done, which was much into the future. And so therefore, Kepler did not know the law of gravitation, and also he did not have recourse to calculus. So when all that was done by Newton, it was possible straight away to calculate what is the mass of the sun. Similarly, we can calculate the mass of the sun, and it turns out to be 3.7 into 3.7 billion times the mass of the sun. There's an object here. But how do we know that the object is compact? First of all, the orbital period here is 15.2 years. Why is the orbital period so short? Because you see all the galactic time scales are billions, tens of billions, and hundreds of billions of years. Okay, so since its birth, the sun has gone around the galactic center only about 20 times. Okay, so here the orbital period is as short as 15.2 years, simply because the star is so close to the gravitating object. And then how close is it? Is that the distance, the shortest between the two, what is known as the pericenter distance, is only 17 light hours, which means that it is 0.6 milliparsec. You see that when people like me see an M there, we always write it as megaparsec. That would be a billion parsec. But here it is milliparsec, which is 10 to the minus 3 times a parsec. Okay, and so the fact that this orbit is so elliptical and the distance is so small means that the object must be very compact. Because if the object were not compact, okay, then it will spread out, then that would affect the shape of the orbit, which it is not doing. There are various ways in which you can try to find out what such a massive and compact object can be. There are some far-fetched possibilities, but the most logical possibility is that it is a supermassive black hole. So now you see that the photometry, let me skip this and go on. And The paper was published in 2003, but the work went on. And then there are the two groups which are working separately on it. They had their own results. I showed you the results of only one group. The results of other group was very similar. And so you see that this is the VLT observations, which means it is done by the European people, very large telescope. And you see that in 2007. This is a adaptive optics image using a detector called NACO. Right? And so now here is the paper in 2009. So if I go back to this paper here, you'll see interestingly that the ellipse is not complete. That is because the object, the time to go around once is 15 years we have seen, and these observations go only over a 10-year period from 1992 to 2002. So when that was done, more observations became available, and in 2009, by then the object was complete, the orbit was complete. But you see that there's a problem here. You'll see that the orbit is not exactly overlapping. Okay, because the accuracy of each point is extremely high. And so you could say that the orbit, as you see here, maybe I showed it. Yeah, you'll see that the orbit is not exactly overlapping. Right? So what is the reason for that? So there you look at the position of the central object. I told you a long time ago, I told you a little while ago in my talk, that radio astronomers have not seen it moving, but here it appears that the central object seems to be moving, which means that it is oscillating around the center of the galaxy, not exactly as the center of the galaxy. And this kind of a movement would lead to this sort of a orbital non-closure, a non-overlap of the orbit. Okay, so that was the feeling. And then again, here is the mass, and then you know the distance of the sun from the galactic center, which is a byproduct of these observations. And what have I shown here is that you see the blue things here are the European observations, and the red points are the observations made using the Keck telescope. The blue ones with the VLT and the NTT, the New Technology Telescope. And then you see that both these sets of points are actually they are distributed in such a way that wherever similar observations in the same epoch are available, there's an excellent overlap between them, and also you get the same trajectory. The points are very well distributed around a single ellipse. So that is very, very reassuring. And then again, here you can see that the ellipse is not overlapping. So now I want to take you, in the remaining 5 minutes for me, take you to very recent observations, okay, which are again produce some extraordinarily good result. So going back to Einstein's theory, 1915, general relativity, then again, many people are familiar with the fact that he made 3 predictions. One was that light which is moving, which is rising up against a gravitational field, must be redshifted. Its wavelength must become redder, and that is known as the gravitational redshift. And then the next prediction was that a ray of light passing into the gravitational field must bend. That's exactly like a passive particle would bend. Okay, and third, that general relativity produces a precession in the perihelion of Mercury. And so what does one mean by this? I'm not going to discuss the other 2 tests because they're not relevant to what I have to say here. Is that, you see, if you look at the orbit of Mercury, forget general relativity for a moment, just look at the observational orbit of Mercury. The Kepler has said that it should be, according to Kepler's law, it should be an ellipse. But it turns out that if you observe Mercury over a long period of time, and why are we talking of Mercury? Because it is the closest to the sun, and so the gravitational field of the sun will be the greatest at that point. So now, if I see the ellipse like this, then it turns out that the ellipse doesn't close at the end of each orbit, and then the net effect is that it is as if over a period of time the ellipse rotates, right? And then therefore, what will happen is that if you take this point here at which the Mercury will be closest to the sun, which is known as the perihelion, and you see that here the position of the perihelion has changed. And what is the rate at which it changes? It changes at 575 arc seconds per century. That's an extremely small change. And uh, how much is an arc second? It is 1 upon 3600 of a degree. So you take the tiny angle, which is 1 degree, and then you take, you know that 1 degree is equal to 60 arc minutes, and each arc minute is equal to 60 arc seconds. So 1 degree is equal to 3600 arc seconds. Right? So this perihelion, the precision of this perihelion is 575 uh, arc seconds per century. And this was not a modern result. I mean, this result was already known in the 19th century. So then people could. It turns out why is this perihelion precessing? It turns out that it the effect of the other planets. The Mercury most feels the effect of the sun, but then there are other planets, particularly a large planet like Jupiter. So that also has the effect on the orbit. And the net effect, the effect of the planets and other similar Newtonian effects, their precision can be added together. It can be calculated extremely well, and it turns out that the total effect is 532 arc seconds per century. So the difference between the observed and that predicted by Newton is 43 arc seconds per century. So the question is, what is this due to? Nobody can find a satisfactory explanation until Einstein came along. And then when Einstein did his approximate calculation in 1915 using his exact equations, but the solution was approximate, and then he wrote down the mathematical expression for the precession which is produced by general relativity. And when you put in the mass of the sun and the gravitational constant and other parameters, you find that the 43 arc seconds, which was not explainable by Newtonian gravitation, was exactly explained by the general theory of relativity. This was a major triumph for general relativity. So now we now have very strong gravitational fields where, for example, in a binary pulsar. So you have got a binary pulsar 1913 plus 16, which was discovered by Hulse and Taylor in 1974. Uh, the paper was published in 1974. These are two neutron stars which are going around each other, and one of them is a pulsar. So this system can be extremely accurately observed because of the fact that it is a pulsar. And then one can show that the orbit precesses. And how much is that precision? It is not 43 arc seconds per century. It is rather 4.3 degrees per year. Such a extremely strong precision. And why does that occur? That occur because the gravitational field, the neutron stars are very compact objects. They're very close to each other. The gravitational field is very strong, and therefore you get this very high precision. Now we go back to our system, which is this system here, the observations of S2. And so these are observations which are made in 1995. These are observations which are made in 2005 to 2010. So on this axis, on the x-axis, you'll see the year of observation. On the y-axis, you will find the RMS uncertainty in the position. The root mean square uncertainty in the position. So the unit is milliarc seconds, and you find that here the uncertainty was several milliarc seconds. Then here the uncertainty had gone down to less than 1 milliarc second, and here it has gone down to tens of tens of microarc second. So you have gone from 10 milliarc second to some microarc seconds, a factor of about 10 to the minus 3 improvement in the accuracy. And what did this come about? It came about because the development of a new detector, which is called gravity, and this uses light from all the four VLT telescopes, and the RMS accuracy is 65 microarc seconds. Using that RMS accuracy, now the orbit has again been calculated using those super accurate measurements. And what do you find here? So you see, first of all, this is not moving. The object, because these were not overlapping, as I told you, the orbit was not closing, and that was believed to be the motion of the very supermassive object. But here, the new observations, you can establish that the supermassive objects are not moving. So then, why is this non-closure occurring? And the simplest explanation, and this turns out to be correct, is that it is precession of the perihelion of S2. Just like Mercury was precessing, the orbit of Mercury was precessing, and then the binary neutron star was precessing, this also is precessing, right? And then how much is the precession here? 12.1 arc minute per orbit. And what is the time taken for an orbit? I told you that it is about 15 years. So 12.1 arc minutes for about 15 years. Okay, so that is the precision. And this is a remarkably beautiful result because it again shows the correctness of the Einstein theory in these fairly extreme circumstances. So here, this is the artist's depiction of the orbit of S2. So which comes there, goes closer, and then goes out. Orbital period is total 16 years here, but we know a little bit shorter. And here is again just a simulation of precession. Because if you start with an ellipse like this, because of precession over a period of time, the ellipse would be swinging in space. So this effect predicted by Einstein in 1915. So we have now measured it in the year 2020. So this paper was again published sometime, I believe, in April or May. And it's again a very beautiful indication of the correctness of general relativity, which came from these remarkably precise observations due to Genzel and Guess and their groups. And therefore, you see the reason for the award of the Nobel Prize. Thank you very much.
Yeah, sir. Sir, it was a wonderful lecture. It was very interesting to know more about these black holes and the kind of work these great astronomers do, and also different imaging techniques of the galactic center and all. So, thank you for this amazing lecture. Also, we have some questions from our YouTube as well as Zoom participants. So, can you answer these, please?
Yes, please.
Yeah. First one is, why does time stop in black hole, and why does a star gets galloped in a black hole?
So you see, it is not that so much as time stops in the black hole. What happens is that when you at the black hole, there's a mathematical singularity. So therefore, you don't know how to deal with it. And that is what Penrose's theorem establishes, that there is a singularity. And our hope is that singularity still could be avoided by violating general relativity. Because the correctness of general relativity as a theory is there. But it has also been shown that if you try to change general relativity within certain frameworks, you still will get these things, whereas other frameworks can avoid the singularity. So it is also possible that when you bring in quantum gravity, this thing may not be there. But that is still to be understood. And why does the black hole swallow a star? So why does the sun not swallow the earth? That is because the earth is going around the sun. Right? Why does not the center of the galaxy swallow the sun? That is because the sun is going around the center of the galaxy. But supposing the velocity of the earth suddenly decreases, okay, then the centrifugal force, you can say the centrifugal force uh, is no longer large enough to oppose the gravitational force, and therefore the earth will fall into the sun. So similarly, a star which is going in a black hole could find that the gravitational field is too large and it can get swallowed. And again, Martin Rees had worked this out. I think it was in the late 70s, just as I was finishing my PhD. And he had considered what happens when such a star goes close to the black hole. And he had shown that the tidal forces of the star just stretch it out, and then it's very spectacular. And those now actually are being observed, those effects.
Yeah. So next is, how can we extract energy from a black hole?
I don't want to go into the details now, but the thing is that nothing can come out of the black hole. But all the methods of energy extraction are dependent upon the spin of the black hole. Because the black hole spin is there and that also has energy, and that could be used for energy extraction.
Okay. What is difference between black holes and a wormhole? Do wormholes exist?
Yeah, you see, I showed you the Penrose diagram, and then if you just consider the black hole solution, then you get only half the diagram, and it can be naturally by taking two reflections, it can be naturally extended, and that is known as a white hole. Just like nothing can come out of a black hole, so nothing can enter a white hole, but things can come out of it. So if you've got a black hole, white hole pair, you could connect them with what is known as a wormhole. Right, so then these wormholes could exist in general conditions, and then you could go into one end and come out of the other end. So therefore, you could end up connecting spaces which are very far away by the conventional way of measuring distances. And that is how, for example, in the Star Trek, how do people go so far, so fast? They do that by using wormholes. But at the present time, these are mathematical constructs and ideas, and it is not clear whether they are physically attainable.
Okay. Um, then what exactly are jets coming out from the black hole? Are they always present, or they are a result of black hole and other celestial body interactions?
You see, they are not really, it is not so much a black hole and celestial body interaction. There's an accretion disk around the black hole and there's a spin of the black hole, which establishes a direction. Then there is a magnetic field which is present there. There are all kinds of plasma which is there. And then the energy which is released by matter accreting onto the black hole is processed in many different ways. I said it becomes hot, but then the electrons can scatter photons, and then you've got synchrotron effect, you've got inverse Compton effect, there are all sorts of things which happen. And then which leads to the formation of these jets. The jets can be extremely narrow, and then they can maintain the direction from micro arc second scale to megaparsecs. And so the jet physics is not completely understood yet. Jets don't always occur. One of the interesting observations is that jets many times happen to be one-sided, meaning don't get them on two sides. But that is considered again to be because, let's say that there's a completely symmetric jet, which one side pointing at you and the other side pointing away from you. Then because of various effects, the one which is pointing away from you is much fainter in appearance, and the one which is pointing towards you is much brighter in appearance. So you see only the bright jet, but not the faint jet. So, I mean, every kind of variation that you can imagine is there in jet physics. But there are a lot of hundreds and thousands of jets have been observed.
Okay. And the last one is from Rupa Kongwad. What is the speed of gravitational waves?
Gravitational waves move with the speed of light. And that was predicted by Einstein in 1916 because he was the one who first predicted the existence of gravitational waves. And then what he did was that he had his equation and he had given an approximate solution of it. And then Schwarzschild gave an exact solution, but Einstein considered another approximate solution and showed that it leads to wave-like behavior. And then he also predicted that the speed of those waves must be equal to the speed of light, the speed of electromagnetic waves. But he himself did not believe in the result that waves exist. He wanted to withdraw the result, but the sort of the genie was out of the bag, and then you cat was out of the bag or whatever, and then now we know that gravitational waves really exist and they travel at the speed of light, and that has been shown to be true to very very accurately from the LIGO observations.
Yeah, okay. So I think questions are over. So thank you once again, sir. And participants can leave now.
My pleasure. Thank you. Can I just log off?
Yeah, or you can wait for some time with us.
Thank you, sir.